I'm Sheng-Wei. I'm currently a PhD student at Purdue University. Today, I'm very glad to introduce our work, Mirror, Model Inversion for Deep Learning Network with High Fidelity. This work is jointly done by Purdue University and Nanjing University. As we have seen this morning, deep learning is very popular. Yeah, I just borrowed this from the Twitter. Yeah. So actually, deep learning has achieved astonishing performance in many different tasks, especially in image classification. You can consider a classifier as a function. It takes in an image and outputs a distribution of confidence over all the labels. There are also a lot of online commercial services providing such classification APIs. Let's first see what is a model inversion attack. Given a model, the attackers don't know the training data or the labels. Their goal is to generate a representative image for a target label and thus causing the privacy leakage. Assume the attacker, in this case, invert this image for a target. Then they can disguise themselves according to the inverted image to pass the classification and cause security breach. There are two settings for model inversion. One is called white box, and the other is called black box. In white box setting, the attackers have the model architecture and weights. They can access the internals, thus they can compute the gradients. However, in the black box setting, the attackers can only get the output confidence. From left to the right, we list the results of existing methods. In each set, the first column is the target class, and the second column is the inverted result. Since it's first introduced in CCS 15, many different methods have been proposed. The black method, AMI, was proposed in CCS 19. The white box methods, GMI and deep inversion, was devised in CEPR 20. While existing techniques have made substantial progress, there is still lots of room to improve. For example, assume we want to invert one target label on a ResNet 50 pre-trained on the VGG phase 2 dataset. We show the target images at the bottom. We can see that the inversions of existing methods are not that human recognizable. As humans, we expect faces should have finer features. They should have higher resolutions. Also, the features should be in the correct positions. Because our method is mainly based on the StyleGAN, so let's first introduce StyleGAN. StyleGAN can generate high-resolution images from random noises called the Z-latent vectors. Its two main components are the mapping network F and the synthesis network G. The network F consists of several fully connected layers with leaky root activation function. It transforms the original Gaussian latent Z space to an intermediate W space. In step 1, we sample Z from Gaussian distribution and apply F on Z to get W. The network G is composed of multiple style blocks with various resolution scales. For example, here is 4x4 to 1024 by 1024. Each style block has two convolutional layers, and the style application is achieved by mutating the means and standard deviations of the feature maps. In step 2, W is duplicated and fed to each style block. Each W is transformed into styles, and the styles are in fact the means and the standard deviations we expect. The obtained styles are then used to adjust the means and the standard deviations of the feature maps in the style blocks to generate the final image. Now let's see how we design our white box inversion approach. We first initialize Z by sampling the Gaussian distribution. And in step 1, we generate W by applying F on Z. In step 2, we use the W to generate styles, and the styles is used to generate the image. In step 3, we feed the generated image to the subject model. In step 4, we compute the classification loss, such as using the cross-entropy loss. In step 5, we use the gradient descent method to update Z. We will repeat the step 1 to 5 until we succeed or reach the maximum iterations. Now let's see how this optimization works. These two images are selected from the target class. In the right, each point in the figure denotes a Z vector. We use PCA to reduce the latent vectors into 2 dimensions. The green area shows the vectors sampled from Gaussian distribution. They correspond to a set of normal images which can be generated by StyleGAN. The gray points show the trace of the optimized z vectors at different iterations. The lighter color means the more iterations. This shows the initialized z. Because it's randomly sampled from the Gaussian distribution, it's located in the green area. For the first 4.8 thousand iterations, the optimization stays in the green area. However, around 4.9 thousand iterations, it becomes a non-phase image. And after that, it's never optimized back to the normal images again. One common trick used in GAN is clipping the vectors into the dense area. Because Z space is normal, so we can clip the values into mean minus STD and mean plus STD. As a result, we can see most of the points are now in the dense area. However, the results are not good enough either. Therefore, we choose to optimize in the W space. W space has been shown more disentangled than the Z space by a lot of existing work. Here, we highlight the difference. So in step 5, we use the gradient descent method to update W instead of going back to the Z. And we repeat the step 2 to 5. Although optimization in the W space gives better results than Z space, the image's quality is still not satisfying. If we apply the similar clipping as we did for Z space, it does not give much improvement. The reason is that W space is not normal, so the simple clipping cannot work. Observe that the left negative part of the distribution looks like compressed. Lots of the negative values are close to 0. Note that the leaky rule will multiply a constant to the negative part of the values. And in this case, if the constant multiplied is less than 1, which StyleGAN uses 0.2, then the negative part will be shrinked. So let's go back to the space before the last leaky rule layer. It's called P space, and it's normal. Now we can apply the clipping in the P space to get a better result. Putting them together, we have a better design of mirrors. So we add an extra step 6 to clip the W in the P space, and repeat step 2 to 6. We can easily generate a batch of images by initializing a batch of W vectors. Now assume we use the current design to invert a VGG16 model pre-trained on the VGG face dataset. Here are 2 real images of the target person. Here shows the inversion result. We find that the natural images are very different from the target person, but the model gives them almost 100% confidence. We speculate that the reason is the model overfits on some low-level features, which leads to local optima. To mitigate this issue, we apply the runtime dropout during the inference time. Dropout layers are usually enabled during training and disabled during inference. Here we insert and enable dropout layers during the inference time. That is, we randomly set some neurons' activations to 0. Finally, we get some correct inversion results. However, there are still some wrong results. How shall we decide which one to return? As we have seen, the confidences here alone cannot distinguish the correct and the wrong images. We observe that the wrong images have more diverse top 5 labels compared to the correct ones. We hence propose to select the result images according to the most consistent top 5 labels. Here we list the top 5 labels predicted by the subject model. We can see that the first and the third images have the most consistent labels, and we randomly return one of them, and that's the correct one. Our black box approach is similar to the white box approach, except that here we use search algorithms such as genetic algorithm to update the latent vectors instead of using the gradient descent because we have no access to the gradient. Please refer to our paper for more details. We mainly evaluated our methods on 3 datasets and 6 pre-trained models. This table shows the accuracy and the input size. When we evaluate our method, we only invert the labels which are not in the StyleGAN string dataset. Because of the time limit, we only show results of our approach and the existing AMI, GMI, deep inversion, and our proposed baselines, which replaces the low-resolution GAN with high-resolution PG GAN in GMI. To fairly compare our approach against AMI and GMI, we trained them on the same training dataset of the StyleGAN we used. For deep inversion, the original implementation starts with random noises, denoted by DIR here. We also tried different initializations, such as the average faces denoted by DIA and the cartoon faces denoted by DIC. Let's first see some qualitative results. The rightmost column shows the real images of the target person. From the left part, each row corresponds to the inversion results of different methods. The numbers in the images show the classification competencies. We can see that our method gives more human recognizable images, and our results are more consistent. This figure shows our white box inversion effectiveness. That is, can the subject model recognize the inverted images? Since they are all white box attacks, you can see most approaches have very high accuracy, and ours is better or similar. This figure shows the white box inversion generalizability. That is, can different models trained on the same dataset recognize the inverted images? For example, the highlighted part means we conduct model inversions on VGG16 batch normalization layer with batch normalization layers pre-trained on the VGG face dataset. And we test the inversion results on the VGG16 trained on the same dataset. You can see that our approach has high generalizability as well. Human studies are very necessary to evaluate the privacy leakage in model inversion. In order to compare our approach against baselines, we conduct a human study on the relative comparison. We want to see if humans think our approach is indeed better than the baselines. This page shows the study example. We show the real image and the inverted images by our approach and another baseline. And then we hide all the images and let the user choose if the left or the right image looks like the target person on the top. This figure shows the human preference of our approach over others. The higher, the better. For example, the highlighted point means on VGG16 model pre-trained on the VGG face dataset, more than 92% users prefer ours to GMI. All of the user preferences are above 50, which means users always prefer ours to the baselines. We also conduct an absolute human study. We mix the images of the target person and other randomly selected people. We test given the inverted image if humans can recognize the target. The average accuracy is about 96%. This figure shows the qualitative results of black box inversion. Each column corresponds to one target person. The first two rows show the real images. The third row and the fourth rows show AMI results and ours respectively. You can see our results are much better. We also attacked online commercial service. We select 8 classes from VGG Phase 2 and use Azure Cognitive Service and Clarify platform to train 2 classifiers. We then use our black box inversion method to attack them. The results show our black box inversion can successfully attack commercial services. To conclude, in this talk, we study challenges in the GAN-based model inversion. We propose StyleGAN-based model inversion in both white box and black box settings. We regularize W latent vectors in P-space. We use random dropout to mitigate feature overfitting. We use consistent top K labels to select the correct inversion. And in the shown evaluation, we can see the images inverted by our method have substantially better quality and fidelity compared to the existing method. And we also open sourced our implementation. You can scan the QR code for our code. And you can also go to our project page to see more results. Thank you very much. Now I will open the floor for questions.